Today, we're going to dive into a data structure that does something that just feels wrong. It takes randomness, something we usually try to eliminate, and turns it into a superpower. Yep, we are talking about skip lists. I know what you're thinking. Randomness, making something faster? It sounds completely backwards, right? But what if I told you that by embracing a little bit of chance, by basically flipping a coin, you could build a data structure that's almost as fast as a complex balanced tree, but a whole lot simpler to code? And that's really the core idea here. The best way to picture a skip list is to imagine your data is one long, single-lane highway stuck in rush hour. What a skip list does is build express lanes right over the top of it, letting you just fly past most of the traffic to get where you're going, incredibly fast. So, Section 1, Express Lanes for Data. Let's dig into how we actually build these data highways.
Okay, here's the textbook definition. Let's just pull out the two most important words here: probabilistic and multiple layers. Probabilistic is just a fancy way of saying its structure is built on chance, not a bunch of strict, complicated rules. And those multiple layers? Well, those are our express lane. To really get why this was such a big deal, you have to go back in time to before 1990. Back then, if you wanted fast, sorted data, you were pretty much stuck with these absolute beasts like red-black trees. I mean, they're powerful, but they are a nightmare to implement, with all these tricky balancing algorithms. Then, William Pugh comes along and basically says, there's gotta be a simpler way. He wanted something that could deliver that same awesome performance on average, but without all the headaches. Section 2, Building the Towers. All right, let's roll up our sleeves and actually build one of these things, layer by layer, so you can see how it all comes together. So everything starts at the bottom, on the ground floor. We just have a simple, sorted, linked list. This is our local road. It connects every single element. Now, for the magic part. For each and every node, we flip a virtual coin. If it comes up heads, bam, that node gets promoted up to a new level. This is our very first express lane. We then just connect that promoted node back down to its original spot, and you start to see these towers forming. And we don't just stop there. For every node that made it into that first express lane, we flip a coin for it again. Heads, it gets promoted to an even higher, even faster express lane. We just keep repeating this process, and what you end up with is this beautiful, multi-level structure. The higher you go, the farther apart the on-ramps are, which means the more elements you can skip over at once. Section 3, the write then down search. So, we've built our data highway. Now, how do we actually drive on it to find something? Well, the search algorithm is just incredibly elegant. Let's say we're looking for the number 37. You don't start at the bottom, no way. You start at the very top, on the fastest express lane you've got. You cruise to the right as far as you can without passing your target. So in this case, the next stop would be 40, which is too big, so we stop at 30. Now we can't go any further to the right on this level, so what do? We take the exit and drop down one level. And now, we just repeat the pattern. Move right until you'd overshoot 37, then drop down. You keep doing this little dance, getting closer and closer to your target with each level you go down. Finally, you get to the bottom level, the local road. You do one last scan to the right and you see the next node is 40. Well, that tells us for sure that 37 isn't in our list. See how simple that is? Right? Then down. That's all it is. Section 4, the magic of probability. So, this all seems a little too easy, right? How does this thing stay so efficient without any of those complex balancing rules? The secret is that coin flip. This is the absolute key. The randomness isn't a bug, it's the entire engine. Those coin flips ensure that, on average, we get a really nicely structured hierarchy of express lanes. We don't have to force it to be balanced. Probability just kind of takes care of it for us, automatically. And this probabilistic approach gives us some really interesting performance. So in the absolute best case, the item you want is right at the front. You find it instantly. Now, the worst case, this is the funny one. This is what happens if you have the absolute worst luck in the world and every single coin flip comes up tails. You just end up with a single, slow, linked list. That gives you ON performance. But I have to stress, this is incredibly unlikely to happen. Because what really matters is the average case. And the average time to search, insert, or delete is O of log n, and that is incredibly fast. Let me put that into perspective. If you double the amount of data, the search time only increases by a single step. It's just so efficient, and it's the same average performance you'd get from a balanced tree.
This is what you can expect pretty much every single time. So what about memory? Does it take up a lot of space? Nope, it's really efficient there too. The space complexity is linear, O of n. If you use a standard 50-50 coin flip for promotion, it works out to about 2 pointers for every element in the list, on average. So yeah, that's very reasonable. Okay, section 5, simple, fast, and useful. Let's bring this all together. What's the practical payoff here? Why should you have this data structure in your mental toolbox? Here's the key trade-off you need to understand. Balanced trees, like red-black trees, they give you a rock-solid guarantee that operations will never be slower than O of log n. But that guarantee comes at the cost of being really complex. Skip lists, on the other hand, are so much simpler to implement. You're basically trading that absolute worst-case guarantee for much simpler code and the same fantastic average-case performance. So if this ever comes up in a technical interview, here are the key things to hit. Start with that express lens analogy. It's super memorable. Describe the right-then-down search pattern, and then nail the complexities. Expected time is O of log n, the super rare worst case is O of n, and the space usage is O of n. You hit those points and you're golden. And this quote from William Pugg's original paper just says it all. The goal was never to be better in every single metric. It was to offer a compelling alternative that delivered comparable speed, but with way less complexity. And he absolutely succeeded. So let's recap real quick. We've learned that we can use randomness to build these towers of varying heights, which create our express lanes. We search them with that simple and elegant right-then-down pattern. And the end result is that we get that beautiful O of log n average performance that we love from trees, but in a much, much simpler package. And that really leaves us with a final question to think about. In a world full of trade-offs, when is probably fast enough actually better than being always perfect? It's a great question, and it's at the heart of so many engineering decisions we have to make every day.